Hello everybody, we have some more inequalities to solve today. Basically it's the exact same process we were following before, just a little bit different. 4 special cases that we're going to run into, and then we're going to practice those for homework, and then tomorrow you will have a quiz to take during quizzes. So, first problem, 3 times 1 minus 2x is greater than 3 minus 6x. First thing we do is write the associated equation. And I'm going to change subtraction to addition at the same time. Now this is an equation, the associated equation, looking for the boundary point. So we solve this equation, remembering the distributive property. 3 plus a negative 6x equals 3 plus a negative 6x. Some of you may recognize that the left-hand side looks exactly like the right-hand side. But in case you didn't recognize that right away, we could continue to try to solve that. And we get 3 equals 3. And the question is, when does 3 equals 3? Always. 3 always equals 3. And what happens to the variable of x? It worked itself out. So in the end, it doesn't matter which value of x is put in there. It doesn't matter what you put in there. 3 will always equal 3. So therefore, all real numbers. Every value of x you can imagine will work in there. It'll always make that inequality true. It doesn't matter. So when it comes to the number line, we don't have any boundary points because they all work. So when I go graph that solution, it's literally going to be all, it's going to be all of those values. Every one of them will work. Every value of x will work, all real numbers. And there's your solution. So that's the first case. First special case is when all real numbers. Moving to the second one, we have the equation negative 2. Try that again. We have negative 2 times 5. That did not work. Negative 2 times 5 plus 6n is less than negative 12n. Again, trying to find the associated equation to get the boundary point. So we write the equation. And solving it, again using the distributive property, coincidentally in the same as we did the first one. Negative 10 plus negative 12n equals negative 12n. Solving that, positive 12n to both sides, and we're left with negative 10 equals 0. And the question is, when does negative 10 equal 0? And the answer is never. This one up here was always, this one is never. And again, the variables dropped themselves out. They work themselves right out of the problem, so it doesn't matter what value of x you put in there, nothing will work. So there are no solutions. This is a case where nothing works. It's an empty number line. It's an absolutely empty number line, nothing. No solution. No value of x makes that, or in this case, no value of n makes that one work. Third special case. Third and fourth are kind of close to each other. Similar problems. The third equation, x squared plus 4x minus 12 greater than or equal to 0. Again, writing the associated equation, making it equal to 0, and solving it. Some of you may notice we have something going on here. For the first time, we have a power of 2. This is a quadratic, actually. It's a one variable, but it's a quadratic. So for that one, we know how to solve those equations too, but you'll need your diamond and your rectangle. Because it's a quadratic, we need our diamond and our rectangle. So again, we have 0 on one side. We must have that in order to solve it. So filling in our rectangle, we have an x squared, we have negative 12, that makes this negative 12x squared. Hopefully by now we know how to do this. I'm assuming we know how to factor. I need two numbers that when I multiply together to give me negative 12, add together to give me negative 4. In that case, it would be negative 6x and positive 2x. Nope, I lied. It'd be the other way around. Positive 6x and negative 2x. Make sure the combination adds together to give us our 4x. So putting those into the rectangle, pull out a negative 2, you can factor out an x, factor out an x, factor out a 6x. Do I have my negatives correct? Yep, I think so. Okay. So then we have, whoops, nope, I don't either. I don't need that x there. Ooh. So we have x plus 6, and we have x plus negative 2. And again, the zero product property, one of these two factors have to equal 0 in order to make the product 0. So x plus 6 equals 0, or x plus negative 2 equals 0. If I solve each of those, I get negative 6, and I get 2. So what does that tell me? These are my boundary points. In this case, I have 2 boundary points. That changes things on our number line. I can, in fact, have two boundary points. One's going to be down here at negative 6. The other one's going to be up here at 2. Now we go through the same process again. Which values of x are going to make this work? Will negative 6 make this inequality true? The answer is yes. Oops, let me get rid of that. The answer is yes, because we want the values that make the left side equal the right side. So we do, in fact, want negative 6 to be part of our solution. So I'm going to put a solid dot at negative 6, and the same thing is true for positive 2. They both make the inequality true. Now, you'll see we have 1, 2, 3 regions we have to test. We have to find out which of those regions work. We have 2 boundary points, so who knows which of those regions will work. So to test the different regions, I'll do it in green. Darn it. I'll get this yet. There we go. Okay, there we go. We want to test. Over here, I have to pick a value that's less than negative 6. So I'm going to choose the point or the value of negative 8. I'm going to test negative 8. So I have to again put it back into my original inequality. These are kind of some big numbers. Negative 8 squared plus 4 times negative 8 minus 12. Is that greater than or equal to 0? I'm going to slide this over a little bit. Give myself some room. Is that a true statement? Well, we have 64 plus negative 32 plus negative 12 greater than or equal to 0. Is that true or false? Well, that's going to be 64 is going to be 32 plus negative 12, and that's going to be, is 20 greater than or equal to 0? And the answer is yes, it does make it true. So I am going to highlight in purple these values over here because they do in fact make it true. Those make it work. Go back to my color green. Now I'm going to test the region in between. Darn it. I'm going to test x equals, and I'm choosing one in between here. So I'm going to choose 0. So 0 squared plus 4 times 0 plus a negative 12 greater than or equal to 0. So I have negative 12 greater than or equal to 0. Is negative 12 greater than or equal to 0? No. This one was true. This one is false. It does not work. So I'm not going to color in. I'm not going to color in those values in between there. Last but not least, I have to test a point over here. So I'm going to test a value of x is equal to, let's choose 3. So is 3 squared plus 4 times 3 plus a negative 12 greater than or equal to 0? Well, 9 plus 12 plus negative 12 greater than or equal to 0. Is 9 greater than or equal to 0? The answer is yes, it is true. So because that works, I'm going to shade these, if I can make it shade. So now I'm going to shade one more time, if I can get this to work. There we go. And I color in those. Now the question is, we need our answer. How do we write the solution to that? That did not work. We need a solution. Box bigger than that. Okay, I'm struggling. Let's do it the other way. So my solutions are all the x's that are less than negative 6 or the x's that are greater than 2. Now something I forgot is I need them equal to as well. So I have all the values of x's that are less than negative 6 or that are greater than 2 and equal to. Those are the solutions for that one. Hopefully that makes sense. The difference we had from yesterday's equations till today are these equations, you remember, have a power of 2. Because of the quadratic, we're going to get 2 boundary points, and therefore we have to test 3 different regions. Hopefully that kind of makes sense. Last but not least, we have the fourth equation, x squared minus 2x plus 2 is less than 5. So again, you'll notice we have a quadratic term right here, so therefore we have to use our factoring again. So our rectangle, come on. And our diamond. So inside the rectangle, whoop, almost forgot. Equation. But guess what? We have a problem here because we have a 5. Remember to use our rectangle and our diamond to factor, we need that to be 0. So the first thing we have to do is get the 5 to the other side. Now we have our equation, and now I can go to my factoring. Make that a little clearer. And that's going to be negative 3x and positive 1x. It doesn't matter how long it takes you to do that, just make sure you can factor. So we have the quantities, finish this first. X, pull out a 1, pull out an x, pull out a negative 3. Make sure that all works, yep. And again, our zero product property, one of these have to equal 0. So x plus negative 3 equals 0, or x plus 1 equals 0. Solving each of those. This should look familiar. We've done it many times. So again, we have two boundary points. Again, we have two boundary points. One is at -1, the other one is at +3. And again, do they make the inequality true? We have to come back to our inequality. Do we want -1 and 3 that make the left side equal the right side? The answer is no. We don't want them because it is not equal to. So therefore, when I graph, I put open dots. I'm going to leave them open. I am not including them part of my solution because this is less than, not less than or equal to. Now I have to go to my testing. Again, I have 3 regions I have to test. So over here, I'm going to test x equals, and I'm going to choose somewhere in between there. How about -2? So I have -2 quantity squared plus -2 times -2 plus +2. Is that less than 5? Four plus 4 is 8. 10. Is 10 less than 5? 10 is not less than 5, so I'm not including it. So this makes it false. Remember, I chose -2 over here, and it made it false. So therefore, I am not going to shade in that region. What am I doing? I am not shading in that region. So then I'm going to test in the middle, somewhere in between here, -1 and 3. I'm going to test 0. And 0 seems to always make it a little bit easier. 0 squared plus -2 times 0 plus 2 less than 5. And now I solve that one. 0 plus 0 plus 2 less than 5. So that's 2 is less than 5. Is 2 less than 5? You bet. It is less than 5. So I should erase those first and then go to my purple and get the size that I want. So I am indeed going to shade, color in everything in the middle, because those did, in fact, again, just to make it clear, I substituted 0 in. 0 is right there. I tested 0, and it made it true. Whoops. Oh my goodness, what just happened? Too many. Yep, we'll get there yet. It made it true, so I'm coloring it. Why is this not working? I'm coloring this in. I'm coloring those in because they did in fact make it true. If 0 made it true, all of them would make it true. Now, I'm back to green. I have to test one more value. Yep, one of these days I'll learn this lesson. Now I have to check a value over here somewhere. I'm going to pick 4. So 4 squared plus -2 times 4 plus 2. Is that less than 5? And we have 16 plus -8 plus -2 is less than 5. Is it? Well, it'd be helpful if I wrote in a straight line, wouldn't it? So this would be 8 plus 2 is less than 5. Is 10 less than 5? Nope, it is not. This one was false. This one was true. This one was false. So again, it comes down to just highlighting for a minute. I can use my pointer. These did not make it true. These did make it true, even though my E erased, and these did not. So this one is false. And therefore, the only ones that work are the ones in between here somewhere. So writing that solution, we could either write x is, what am I doing? Greater than 1, and it has to always also be true that x is less than 3. Hopefully we remember how to write inequalities. Hopefully. x is greater than 1 and less than 3. Some of you may prefer to write that as a combined inequality. This one is probably the preferred answer. So again, we graphed our solution, and then we also wrote our solution. And again, just in summary, we're trying to find the values that make the inequality true. And in all of these cases, except for this one, the no solution one, in all of these cases, they had infinitely many solutions. Solving inequalities almost always gives infinitely many solutions. And we draw the picture rather than list all of the solutions. Hopefully that worked a little bit for you. Can get kind of messy. Probably should have drawn lines between all my work. I'll get better at this as time goes on too, trust me. There are all the 4 problems. So, there you have it, solving inequalities. Talk to you soon. Bye-bye.